So last time, what did we talk about? We talked about quantifiers. So I want to do a little bit more on quantifiers right now, and then we're going to talk about implications. Okay, so I'm just going to do a little bit more on quantifiers. So this is kind of a warm-up from last time. So let's consider the proposition, the following. So for every integer, the integer is less than 0, and it's a square as an integer. Let me just move this over. X is equal to y squared. Okay, so this says in English, every integer is negative and a square. Okay, so let's try and rewrite this so that this quantifier can be written on the outside. Okay, so we will rewrite this formula. So the existential quantifier is on the outside. Okay, so let's I'm going to introduce some more notation. Okay, so I'm going to introduce some symbols. So let p of x. So this is a predicate. So this is going to be this predicate x is less than 0. Okay, and then I'm going to do another one, q of xy. Okay, and this is going to be defined to be equal to x is equal to y squared. Okay. So I introduced two symbols here. So sometimes when there's two things in here, the two variables here, this two variable predicate is called a relation. And we'll talk more about that later, but I just wanted to point it out. Okay, so this is like a two thing. You plug in two numbers, it'll return true or false. Okay, so so the inner statement, let's look at the inner statement. So the inner statement of our formula is the following. So I'm just going to rewrite it over here. So it's that there exists. So it says x, or so it says p of x, and there exists a y. So I'm just going to omit the universe here. I could do y an element of z, but I'm going to take it to be understood, such that x is equal to y squared. Okay. So that's what we had. That's what we have for the inner part of this without this outside quantifier. So this is with a free variable x instead of a bounded variable x. Okay, so so we talked about how the two quantifiers were related to and or. Do you guys remember that? So the existential quantifier, so that's related to or, and the for all, or the universal quantifier, is related to and. Okay, so this thing looks like, so another notation that we had was like this. So it looks like a big disjunction of these things. So we had this big or, so we had this and, or sorry, so p of x and this thing here. And so we had that this, last time we talked about distributive rule, and for quantifiers we have the same distributive rule. This distributes over this big OR. Okay, so that's how it's going to work. So this thing is the same thing as OR y. So this big OR of p of x and x is equal to y squared. Or, in the other notation, right, so now from here to here is where I use the distributive rule. Okay, so there's a distributive rule over these quantifiers. Okay, and so this is the same thing as saying that there exists a y such that p of x and, oh, sorry, I forgot to do q of xy. So q of xy. So I meant to write q of xy all down here, but I just didn't do it. Okay, so this is kind of a general thing. So I could have written, so let me take a second, and I'm just going to put q of xy over each of one of these. That's what I meant to do, but it doesn't really matter either way. But I just wanted to substitute this with a general thing so it looked more general rather than our particular proposition. Or a particular, proposition with variables. Okay? So does that make sense? So how we can distribute this? So our original formula here, so the original formula is the following. So it's the same thing as for all x and z. So there exists a y and z such that, so p of x and q of xy. So x is less than 0. And we had that x is equal to y squared. Okay, and so this is how, and if you wanted to, you could write this with a comma here instead of those parentheses like that. Okay, so this shows you how you can move this quantifier from being isolated in this little piece here to the outside. Okay, so it's just that. That's all it is. Okay, so there's the other rules. Let me just write down now all the rules that we have for distribution. Okay, so here are the rules for distributing quantifiers. With quantifiers. Okay. Okay, so we could have and there exists a y such that q of xy. Okay, I'm just going to write down all the possible combinations where we have a connective here and then a quantifier here. So p of x and there could be a for all here. Okay, and then I'm going to leave space to leave space because I'm going to write what it's equal to over on this side. Okay, so now we could do p of x or p of x or, and then we could do an existential quantifier. And this is a general thing here. And then for all y, q of xy. And it doesn't matter the universe here. This is just a general thing. Okay? So this is the one that we just talked about. Okay? And it distributes the following way. So p of x and q of xy. Okay? So same thing with this one. So this one's for all y, p of x and q of xy. This one's there exists a y. And so you can just distribute this too. So for this is like a big OR, right? You might as well have the OR in every single term. So p of x or q of xy. And then here, same thing. You can distribute again. So this is for all y. And so this is like the distribution of or over and. I guess the more interesting ones are or xy. Okay, so we have these two things. So these are the rules for distribution, like this. That's all I wanted to say. So that may help you sometimes when you have a formula and you want it to look like it has quantifiers on the outside. You can do that, okay, by using these rules. Okay. So any questions on that? Okay. Okay. So I'm going to talk about implication now. Okay. So I'll start on this board here. Implication. Move this over a little bit. So this is a new connective. And these are the if-then statements that we're gonna deal with a lot. So implication. Okay. So let me give you some examples, right? So if n, so this is going to be a statement about the integers, say, if n is even, then let's just do it like a sentence. Then n squared is even. Let's break it here, I guess. Is even. Okay, there's one sentence. Okay, that's an if-then statement. So if there's free food, if the food is free, then I will eat it. Okay, so there's one. Okay. Okay, and so there's a symbol for that. So given P and Q propositions, in general, Q propositions, we form a new proposition. A new proposition. And the symbol for that is like so. P implies Q. Okay? And so there's a bunch of different English words we use for this. So if P, then Q. Sometimes it's called to be Q only if P. Or sorry, P only if Q. Or it's P entails Q. Or whenever P, we have Q. Okay, so there's a bunch of different ways of saying this. And so we need to give it an official logical definition. Okay, and the official logical definition will be as follows. Okay. Yeah.
Would it be P only if Q or Q only if P?
So P only if Q, because so Q is a consequence of P, and so if P appears, Q needs to appear. I get confused on that sometimes, but yeah. I had to think about it for a second. So because of this kind of confusion, right, that can occur, we give it an official definition. Yeah?
So this is saying that if P exists, then Q does exist?
Yeah, so let me give you the official logical definition. So we don't want to get wrapped up in the words, so I'm going to give you the official definition. Okay? So the official definition is the following. Okay, and the official definition has some weird consequences that you wouldn't consider normal in English. Okay, and we'll talk about that in a second. So the definition is the following. So P implies Q is defined to be not P and not Q. Okay, so what does that mean? So it means like you're not going to have the situation where you have P and not Q. So that's why I say P only if Q, right? So you're not going to be in the situation where you have, you're going to contradict this. So P and not Q is not going to be a thing, okay? So so here's a little exercise that we'll do together, okay? So here's an exercise. And I want you guys to do this too. We'll do it at the same time. Okay, let's compute. We'll have a race. The truth table for P implies Q. Okay? So you guys take out a piece of paper or do this in your notes, like on scratch work or something, and I'll do it with you guys, okay? And we'll see who finishes first. Okay. Okay, I'll give you guys a little bit of time to finish it. So I'll stand in front and make sure you guys try and do it. I know. Okay, so I did this one first, and then I negated whatever this was. So that's how I did it. Okay, so this is what I ended up getting. Okay, so like they're all true, right, except for this one, right, where P is true and Q is false. Okay, so that's the name of the game, right? So this is what it is. Okay, note in particular that something really weird happens, right? So remark. So what's the weird thing that happens here? So the weird thing that happens is that so P implies Q is true, provided, let's say, whenever P is false. Okay, so something false implies whatever. Okay, so in particular, when P is false and Q is true, it's still true, right? And when P is false and Q is false, it's still true. Okay, so and when they're both true, it's true. And when P is true and Q is false, that's the only one that's not P and not Q. So like that's the one where we get it's false. Okay, so this is exactly when we have P and not Q, right? Okay, so does that make sense? So let me show you why this is weird. Okay, so like now we're going to use this, and I'm going to show you something that's kind of not as intuitive. So let's consider the following example, the following sentence. So if 2 plus 2 is equal to 5, so whenever 2 plus 2 is equal to 5, then 1 is equal to 0. Okay? So is this statement true or false? So whenever it's true, right? So whenever 2 plus 2 is equal to 5, 1 is equal to 0. 2 plus 2 is never equal to 5, right? So whenever that happens, sure, right? But it never happens. Okay? So that's why it's true. Okay? So so here we have, this is the statement, here. So 2 plus 2 is equal to 5 implies 1 is equal to 0. So like in the comment here, this is something that's false implies something that's false, right? Which is true. Okay, so that's a true statement. Okay, so you just have to be aware of this, and this is the convention that we make. Yeah.
Is that the bottom row of the truth
That's the
table?
bottom row of the truth table.
Okay.
Exactly. That corresponds to the bottom row of the truth table. Okay. So that's how the truth table for this thing breaks down. Okay. And now I'm going to talk about two associated implications. Okay? So there's the converse and contrapositive.
So can Q exist without P?
No. Let's say, yeah, Q can exist without P for sure. Yeah.
Exist without
Exactly. Yeah. P only if Q. Exactly. Exactly.
Okay.
Yeah.
Okay, I understand.
Yeah. Q can be okay on its own, right? Yeah. So like here, if P is false and Q is true, then it's okay still. And that's what you were asking.
So would this idea be kind of like P is contained in Q?
Yeah. So P entails, that's what I was trying to do here. So P entails Q,
Okay.
right?
Okay.
So that's why I wrote this one.
So it's like a circle and then a bigger circle around it.
Yeah, if you want to think of it like that, right? So, okay. So here let's talk about the converse and the contrapositive. Okay, so I'm going to give you the definition of the converse. So the converse of P implies Q is the implication Q implies P. So you just flip the arrows. So P implies Q and Q implies P are not the same. Okay? So the other one is the contrapositive. And the contrapositive is a very useful thing. So the contrapositive of P implies Q is the statement not Q implies not P. Okay? As a spoiler, this one is equivalent to P implies Q. This one is not. And this one is extremely useful. So let me give you some examples. Okay? So let's do an example here in words.
So the contrapositive is equivalent to the implied.
Yeah, so we were going to use the contrapositive a lot. So when we want to, so sometimes we'll do something and we want to be able to prove P implies Q, right? And it'll be useful to think about it as not Q implies not P sometimes, as you'll see. So let me show you. Let me give you, let me just give you an example to kind of solidify what I'm saying, right? So if n is a prime bigger than 2, then n is odd. Okay, so this is our statement of P implies Q. So P is that n is a prime bigger than 2, and Q is that n is odd. Okay? Okay, so let's look at the converse of this statement. Okay, so the converse of this statement is what? It would say if n is odd, then n is a prime bigger than 2. So like, this statement is false, right? This statement's true, right? You can just, we know it in our hearts it's true. It's like 3, we didn't prove it, but it's true, right? 3, 5, 7, 11, so on and so forth, okay? But this statement here is the converse of statement, the converse of that, and it's false. 9 is an odd number. 9 is 3 times 3, and it's not prime, okay? So that's a counterexample to this statement. Okay, that's how we can disprove it, is by finding a counterexample. Okay, so but let's look at the contrapositive of our statement. So the contrapositive. Okay, so the contrapositive is, okay, not Q implies not P. Okay, so not Q implies not P. So if not q. So not q, if n is not odd, then n is not a prime number bigger than 2. Does that make sense? Because it'll be divisible by 2. If it's even, if it's not odd, it's even, right? It'll be divisible by 2. And this one, you can see, is equivalent to the first one. You can just look at it, and it makes sense, right? Okay. Okay. So now I'm gonna show you the proof of the logical equivalence of P implies Q and Q implies not Q. The logical equivalence with the contrapositive. Okay. So let's start in on this. So. Okay, so my first claim is that, so P implies Q, claim. So P implies Q is logically equivalent to not P or Q. So this is period, this is a not, so I mean not P or Q. So it's not the whole thing. So it's not P or Q. Okay? So let's prove this. Okay, I'm gonna give you guys a proof of this. Okay, so here's a proof. Okay? So so P implies Q. I'm going to start with this statement here. And so let's apply the definition. So what was the definition of P as implies Q? So it was not P and not Q. So not P and not Q. Okay? Okay, so now this is, let me write down the steps. I'll write the steps of what I'm using over on this side right here. So this is the definition of the implication. Okay? Okay, now the next step, so this little thing in parenthetical will be an explanation of this equality. Okay, so now we can use De Morgan's laws. Okay, so De Morgan's allows you to distribute and flip. So this is not P or not Q. So this is by De Morgan's. Okay? Okay.
Would you have to do the not? It wouldn't be good.
They do cancel. I'm just being really careful. Yeah, you're absolutely correct, right? And that's the next step. So this is not P or Q, okay? And so this is by double negation. Okay, so double negation is this thing. And this is what we wanted to show. We wanted to show that P implies Q was logically equivalent to this one. And we used our rules of things that we knew that were logically equivalent to arrive at this conclusion. Okay? Cool. Okay, so that's the end of this proof. Okay, so let's do another one. Okay, so here's another claim. Okay, so the claim is that P implies Q is logically equivalent to the contrapositive. Logically equivalent to not Q implies not P. Okay. So here's what we're going to do. We'll do the proof up here. All right, let's do the proof. Okay, so P implies Q. Or let's see, how do I want to start this? Let's start with not Q implies not P. Okay, so let me do a little substitution here. So this is A implies B, where A is not Q and B is not P. So we'll do this implication. So letting this be true. Okay, and so this was not P, or not B, or not A, and not B. Okay, so we're using, this one here follows from the definition of implication. Okay, and so I'm going to just substitute this in again. So I'm just going to do not. And so the definition of A was not Q. And the definition of B was not P. So not P. Okay, so we have this statement here. Okay, and so we could have just gone from here to here if you could see the substitution right away. But I just wanted to show you what I was using. Okay? So now what is this one here? So this is not Q and P. Okay, so this is, I used double negation here. So this is a substitution, sub for A and B. And then this was double negation. Okay, so I got rid of the not there. Okay, and so now let's use, for this line, we'll use De Morgan's again. So this is equal to, okay, so we'll distribute this. So this is equal to not Q, and turns into an or, not P. Okay, so this is Q or not P. Okay, and now what is this one? So this is here. This line here used De Morgan's, and so this again we use double negation, and then here this is P implies Q. So this is the previous claim. Does that make sense? We used this thing here. Oh, no, sorry, this one. That this was the same thing as this. Okay, so this shows this string of inequalities, or equalities, sorry, not inequalities, shows that not Q implies not P is equal to P, is logically equivalent to P implies Q. Okay, so that these two propositions are the same. Okay, so and this is how we show it. Okay, and that's the end of that. Okay, so that's this proof. Any questions on that proof? Okay, I just used the rules over and over again. Yeah.
Anytime you get like Q or not P, you can just go automatically to P and Q.
From this one, you mean? Q
Yeah,
or not P?
Yeah, you
Yeah, I proved it here.
Okay.
So then I can just go to it. Yeah. So this is a proof assuming that I know this.
Okay.
Okay? Yeah. And which I did show. Okay. So let me just make a remark here, and I just want to write it on the board, is that the contrapositive, so the contrapositive is very useful. So just a remark, the contrapositive is very useful for showing P implies Q sometimes. Okay, because the psychology of it sometimes changes when you look at it in the contrapositive and something clicks. They're equivalent, right? But sometimes it's easier to see what's going on when you use the contrapositive. Okay, and so let me just make a quick remark on negations, and then we'll do some exercises. Okay, so let me just say what it is. So not P implies Q. So that's the negation of P implies Q, right? So why don't we just plug in the definition? So not, and the definition of this is not P and not Q. Okay, so the negation, so we just use the definition here of implication. And then here, we have a double not. So the parentheses don't really matter. And so this is P and not Q. Okay? So to show that P implies Q is false, we need to get a situation where we have P and not Q. Okay? So this says to show that P implies Q is false, we need to give a situation where we have P and not Q. Okay, so we need to start with a P. So often it comes in the form of an example, a counterexample or something. So we'll have a P, and we need to show with P having, then you have not Q. Okay, so so here are some exercises that we'll do that will hopefully clarify what I just said. Okay, so exercises. Okay, so handout 1. And so in handout 1, I want you to do the following exercises. So exercise 3.6, exercise 7, all of them, and then we'll do exercise 9.7. Okay, so we'll do these together in class, and then I'll come around and help you guys.